Okay, let's see what happens. So suppose the original, this is normally how we think when we are stuck, when we want to design a reduction rule and we don't know what kind of a reduction rule we should be designing. This is one way that we usually think. We think about it like this. Okay, suppose if it was a yes instance, then what would happen? If this was a yes instance, that means if G had a vertex cover of size at most k, then how would G look like? Okay, so this is if I can't see the vertex cover of size at most G. This is all the thought process. Okay, the algorithm is not doing all this. This is how we are thinking. So if G had a vertex cover of size at most k, look at that vertex cover. Again, we can always look at it imaginatively. The algorithm is not looking at it. So let's say that vertex cover is x. Its size is at most k. When we delete x from the graph, what do we have? Independent set. So the other vertices, this is an independent set in G minus x, right? Okay. So now, okay. So why is the size of this graph not bounded? The size of x is anyway at most k, right? So why is it not bounded? Because there are a lot of vertices here, right? So somehow we have to figure out, in some sense we have to figure out these vertices and try to reduce their size, like try to get to an instance where even after the removal of the solution, you don't get a lot of such vertices. Okay, so let's see what we can do. We know that we have applied this degree 0 rule. Okay, so it can't be the case that this vertex has no neighbor at all. This vertex definitely has no neighbor here, but each of this vertex has to have neighbor up there, right? Every vertex has a neighbor up there. So what does that mean? If the size of x is at most k, okay, can you say, and each vertex sees something in x, can you bound the size of these vertices with a function of x and something more, like some property of x? Like for example, suppose I knew that each vertex in x had small degree, has say degree d. Then what can you say about, then how many vertices can be there here? Sorry? X into d. So this is, suppose I tell you that for all x in x, degree of x is at most d, then what will be the size of G minus x? At most dx. Why? Because look at any vertex, it can have d neighbors below. Okay, so in total these vertices can have dx neighbors below, and each vertex is a neighbor to some vertex because it can't be isolated. If I didn't apply this isolated vertex rule, there could be a lot of vertices and then I can't bound the size of this set. Okay. But with this set, we have this. So one observation is, if somehow I can reduce the degree of every vertex in the graph, for example, in particular, it's enough to reduce the degree of the solution vertices, but I don't see the solution vertices, right? This was all in our head. So one way is, if suppose, like it might not work for every problem, but this is a starting point. So suppose we can reduce the degree of every vertex in the graph somehow. Like if we have a reduction rule that says, okay, if there is a vertex with large degree, then do something. If we had this kind of a thing, and eventually, when we are not able to apply the reduction rule, the degree of every vertex is bounded by d, then what can we say? Then do we have a kernel? Other words, we'll design this rule. Suppose I have another reduction rule. So I'll usually write reduction rules by RR. So this was reduction rule 1. So suppose we have reduction rule 2, which says that if there is a vertex in VG whose degree is strictly greater than d, say, then let's say, as of now, let's say the reduction rules deletes this vertex from the graph. So it creates another instance and something will happen there. We'll figure out what happens there. But suppose if whenever it finds a vertex of large degree, it deletes from the graph And suppose I tell you this is a safe reduction rule. I've not defined what D is, I've not defined all these things. But suppose I can always do something. If I find a vertex of large degree, I can always do something. So that means if I have a vertex of large degree, I'll do something. And when do I stop? I stop when I'm not able to apply any of the reduction rules. In particular, I'll stop when there is no vertex of degree 0 and there is no vertex of degree greater than D, right? So every vertex will have degree less than D, right? So now let's see. Now, if after the application of this reduction rule, so let's say after the application of reduction rule 1 and reduction rule 2. When I say after the application, I actually mean after the exhaustive application, which is, see, when you apply this rule and then you apply this rule, after the application of this rule, you might get some new degree 0 vertices and then you might have to go apply this rule again. And you keep on doing it. And you stop after the application of this reduction rule. What is the property of the graph? Let's say after the application of this reduction rule, we get an instance G star K star. Because these reduction rules are safe, I'll prove the safeness of this. Because these reduction rules are safe and equivalence is a transitive thing, I know this is an equivalent instance to GK. Right? So anyways, I only have to solve the problem on this. So what I know is after the application of this rule, if this is the reduced instance, then I know that this instance has no vertex of degree 0 and no, it is not the case that there exists a vertex of degree 0 and it is not the case that there exists a vertex of degree greater than D. Okay? And we had just seen that if it was a yes instance, this like the algorithm is not doing anything, this is just an observation. If it was a yes instance and if we had applied these and if the we know that every vertex has degree at most D, then in particular the degree of vertices of X will also be at most D. So the number of so the total number of vertices that these vertices of X will be seeing here will be at most D into X, and there are no isolated vertices because of this rule. Then what can we say? Sorry? X has to be greater than X, wait, X has to be greater than Y. So this is n minus x by d, yes. Yeah, so does this give anything? Yeah, yes. So it's again the same argument. So if it's a yes instance, okay, then we know that G minus X has size D minus X. Okay, you don't really have to do that also. So let's see then what is the size of G, then how many vertices are there in such a graph G. The vertex set of G can be divided into two parts, X and vertex set of G minus X, right? What's this, how many vertices are there in X? Some K, right? So at most K. And how many vertices are there in G minus X? So again, what have we proved? If it was a yes instance, then the number of vertices better be bounded by this number, right? And basically, so what we do is we apply these reduction rules and then we just go check the number of vertices in the input instance. If it is greater than this number, then what do we know? This is the contrapositive. We proved if it's a yes instance, then the number of vertices are at most this. Contrapositive of it is if the number of vertices happens to be more than this, then that's a no instance. So after the application of these reduction rules, we just go check the size of, so we just go check the size of like the number of vertices in Vg star. If it is greater than k plus dk, we know it's a no instance. In this case, just return a trivial no instance. Otherwise, what do we know? wait, yeah, makes sense. And see, let's try to understand what is really happening here. So, let's try to understand. So, of course, we have seen it formally, but let's also try to intuitively understand why is it that if the reduced graph has a lot of vertices, we are able to say no. Okay. See, look at, suppose you have a graph, and if the graph had a k-size vertex cover, okay, or in other words, look at any vertex. How many edges can a vertex cover? Cover as in, vertex cover covers the edges of the graph, right? So a vertex cover, like every edge of the graph has to be incident on some edges, some vertex of the vertex cover solution, and any vertex cannot cover more than its degree many edges. Right? Or degree many edges as in, let's look at the correspond, like, so it cannot cover, yeah, degree many edges. If you are looking for a vertex cover of size k, and if I know that in the graph every vertex has degree d, then how many vertices can, or how many edges can this k size vertex cover? Kd. So clearly if there are lot more vertices than kd, how are they ever gonna be covered by k vertices? This is all because of the fact that the degree of each vertex is bounded. Of course, if the degree of a vertex was large, it could cover a lot of vertices, but its degree is small. So this is exactly what is happening here. So if the number of vertices is very large, then we know no k-size solution will be able to cover it, because every vertex has degree d. It can only cover at most d things, right? So this is why, like, this is the intuition behind why this is holding. And if this is not the case, this is bounded. Make sense? So we are yet to look at the reduction, like what is this reduction rule? How can we bound the degree of the vertices? It looks like this is the crucial part. If we can't bound the degree of the vertices, we don't know. Okay? So let's see. So, okay, let's see if we can come up with why such a thing should hold. So what do you want to say if there is a vertex and it has a lot of neighbors? We want to say something like we want to say that, okay, then you can throw it. So that sort of a rule is what we want to make. So note that we are looking for a vertex cover of size at most k. So okay, let me just make this task easier for you. Suppose there is a vertex of degree at least k plus 1. Okay, so I fixed d for you. Suppose there is a vertex of degree at least k plus 1. What can you say about this vertex? You're looking for a solution of size k. Yes. Yeah, so this is a property of vertex cover. No matter what the degree of the vertex is, either that vertex has to go to the solution, or if it's not going to the solution, all is important, right? Yeah, all its neighbors should go. Now I give you a vertex with degree k plus 1, and you're looking for a solution of size at most k. What can you say? Sorry? Yes. So there is no vertex cover of size k that avoids picking this vertex, right? So basically we are trying to design this reduction rule. If suppose the degree of every vertex is strictly greater than k, so it's at least k plus 1, then what do we know? This vertex has to participate in every vertex cover of size at most k. So what we do is, so we know that whatever solution we are looking for has to pick v. In that case, we just delete v from the graph and reduce k by, right? So, okay, let's quickly prove the safeness. So basically, when we say this arguments, of course, it looks correct. There is a vertex which is present, which will be present in every solution, so it's okay to delete it. But when we do things formally, like we actually have to prove the safeness of this reduction rule. For that, we have to prove like both the directions, in the sense that if this had a vertex cover of size k, then you have to show me a vertex cover of size k minus 1 in this graph. And if this has a vertex cover of size k minus 1, you have to show me a vertex cover of size k. This will formally prove the correctness, right? So let's just quickly see. So if this has a vertex cover of size k, will this have a vertex cover of size k minus 1? Why? See, you give me some vertex cover of this graph. Let's see why is that vertex, okay, wait. So okay, suppose you give me a vertex cover S of this graph. Is S a vertex cover here? Or in other words, let's go to a more general thing. If suppose there is a set of vertices which is a vertex cover for a graph G, then are those vertices a vertex cover for any subgraph of G? Because this set, all the edges of the graph are incident on some vertex of here. In particular, all the edges of the subgraph also will be incident on some vertex for here. Of course, when you look at the subgraph, look at S minus whatever, like S intersection whatever is there in the subgraph. So, if S is a vertex cover here, S is definitely a vertex cover in G minus V. Because G minus V is nothing but a subgraph of G, right? But the problem is S was a K size vertex cover here, and you have to give me a K minus 1 size vertex cover here, right? So how will you do that? See, again, this formal proof is nothing but what we just nodded a minute back. We were all convinced that this reduction rule is safe, right? Why did we all nod it? We all agreed, and believe me, there is nothing more to it that I'm trying to prove. Exactly. So whatever solution you give me, no matter what solution you give me, V has to be present here, right? So V is present here, and in this graph I have deleted V anyway. So S minus V is a vertex cover in this graph, right? Because V has anyway been deleted already, right? So if this had size K, this definitely has size K minus 1, and this is a vertex cover here. So this proves the forward direction. For the reverse direction, suppose I give you a vertex cover S prime of this graph of size K minus 1, then can you give me a vertex cover of size K here? Sorry? Yes. So if S is, let's say this is S prime, if S prime is a vertex cover here, then S union V is definitely a vertex cover here, right? It has size K minus 1, it has size K. So this is how you prove the formal correctness. So basically what we have proved is degree of V, if degree of V is strictly greater than K, then we can do this. So that means after the application of these rules, every vertex will have degree at most K. So basically, what is the size of the kernel that we get? D here is K. So you get K plus K square kernel. So some order K square, right? But again, when we are giving a kernel, we have to bound both the vertices and the edges. So can someone quickly bound the edges? Any bound will work as of now. If the number of vertices in this graph is order K square, can you say anything about the number of edges in this graph? Sorry? Sorry? K cube by 2. Why? Sum of all the degrees by 2. Yes. Okay. So, oh wait. Okay, so there are K square vertices, and each vertex has degree K. So sum of all the degrees is at most K cube by 2, right? You were saying something. So definitely the number of edges in this graph are order K cube. But you can even prove that the number of edges in this graph are order K square. Can someone, you were saying something? Okay. But again, I think I'll just leave the class here. So it's anyway there in your tutor. It's nothing more than, like, everything is there. So just try to prove that. So we anyway have a polynomial kernel. This we all agreed, right? As he said, the number of edges in this graph is K cube. Even if you don't want to do anything fancy, look at an n vertex graph. How many edges can it have at max? N choose 2? N square? So definitely this graph has order K per 4 edges. So you definitely have a polynomial kernel, right? Just try to convince yourself that this graph actually has K square edges. I just leave that as an exercise. It's not difficult.